the US government decreed the prohibition, which was a constitutional ban on all sorts of alcoholic products. While this did help in decreasing consumption overall nationwide, it did not fully stop it. Instead, people set up illicit shops and places where they could secretly and in the comfort of their privacy consume a drink. Welcome to Speakeasy, our talk. In our world, Speakeasy is a place where you can secretly and in the comfort of your privacy operate on data. My name is Manohar, and with my colleague Jakob here, we're going to tell you a little bit more about this library. What is Speakeasy? Well, it is a library that allows you to do privacy-preserving computations and combine multiple different privacy-preserving techniques to write privacy-preserving programs.
One of these techniques, in fact, the main technique we use in Speakeasy is called secure multi-party computation. We gave a talk about this 2 years ago at the Scala days. If you want, you can look up that talk. I'll give you a quick refresher. Briefly, it is a subfield of cryptography with the goal is to compute the output of a function without revealing the inputs. As an example, I'll give you this specific use case here. We have 3 people, Dimitar, Jakob, and Manohar, who have a secret number, A, B, C each, which they do not want to reveal. This could, for example, be their salary. Yet they all want to compute the result of the sum of these numbers to, for instance, calculate an average. So how is this done? In the simplest sense, every party generates 3 secret numbers that sum up to 0, but that are each random. They then distribute each number to another party, keeping 1. This yields the sums S1, S2, S3. They then sum up all data publicly to reveal the sum of all numbers. This is possible because we know that the individual secret shares all sum up to 0. So in the end, you get the sum, the aggregate output of all inputs without knowing who contributed what. An example is this image here. We have two secret images, and you combine them, and you get a revealed result. Now, this is for addition. Of course, there are many other there are more techniques which allow you to approximate, in fact, any function as long as the input data is numeric, and you can get pretty far with any classic machine learning techniques now in a privacy-preserving manner. In our case, we can always summarize the setup, which you'll see in the rest of the talk, to be divided into the following parties. There's an analyst, which submits data to some owners. You can see the owners, the 3 little people here. There's a runtime, which orchestrates some flow of information. And sometimes there's also another third party, which is a source of randomness that's introduced.
So, as Jakob has said, right, MPC allows you to approximate any function. So you can do a lot of things, a lot of interesting machine learning things. But in general, MPC may not be enough, and for different reasons, really. Simply, one thing is that data does not live in a vacuum. To get into MPC, you need to approximate, or you need to first convert your data into some numeric form. So this numeric conversion needs to happen outside of an MPC context. So you need to potentially do some sort of local processing to get it done. There are maybe other techniques that are more useful in your setting, where MPC might be just helping you in part of your privacy-preserving computation. Maybe you want to chain it with fully homomorphic encryption, or maybe you want to combine all of this in a federated learning setting. So let's look at one example where we think MPC is not enough. And this is a very simple one, which sort of gives you a very basic idea of why you want more. In data processing pipelines, and even in general plain text ones, one thing that people often do is they convert categorical data into numeric before running a machine learning algorithm on it. And a classic way to achieve this is called one-hot encoding. So given a set of categories, or given a complete set, what you do is you create a mapping between every single element of the set into some number. So how do you do this when you don't know the full category? Let's say that I only know half of this category, a portion of it, and Jakob knows the other ones. At this point, it's not enough for me to make a one-hot encoding of my own data, because I need to know what the full category is. So at this point, we need to come up with a protocol whereby we first exchange some information, which allows us to complete the full set of the categories before we can compute the one-hot encoding. And this is, of course, all done before we even enter an MPC algorithm.
So now let's talk about what Speakeasy exactly is. We've kind of given some hints, but to define it concretely, Speakeasy is a Scala library for building, composing, and executing any kind of privacy-preserving programs that you want. It's based on the concept of private distributed data sets, which we'll elaborate in a little bit. And it really is a DSL which composes different kinds of DSLs. So it allows us to work on composing algorithms that are defined in the multi-party world with things like Manohar just mentioned, plain text, and potentially in the future, even other technologies. Important thing to note is it allows us to define these things, but it does not make any assumption on the concrete runtime. So this allows us to switch in runtimes, potentially reusing, interfacing with existing systems out there. What we'll do now, to give you some feel of it, because this is a lot, we'll start from the top. So we'll look at how Speakeasy looks like for a user, and then try to work our way backwards to the individual concepts. So in this code, there are two things you should pay attention to. Don't worry about understanding all the types yet. The first thing to note is the general structure. So what we're doing is we're defining a pipeline of computations. This is divided into sourcing data, so instructing the program to say, read data from somewhere, from some owners, then running some computations on it. For example, this is a local computation, followed by a computation in the multi-party realm, but we're not running it yet. The running happens later on in what is the red thing here. So that's the first thing to note, this distinction between defining a pipeline and running something. The second thing you should note on Speakeasy here, the second noteworthy feature is that we're composing languages. So on the high level, this is general Scala code. You know, we're defining just, you can use whatever, data structures we would like. But inside this multi-party block, so this part here, what you see here is actually a separate DSL that could not exist outside of this block. Now we'll get into explaining how this works.
So where does one go to Speakeasy program? Let's look at the general flow of executing a privacy-preserving computation. So taking all the actors that Jakob introduced to you, the flow is as follows. You have a data analyst sitting somewhere outside who wants to wants to execute a computation. And they would do it generally using a client. It could be a web client or something like Python, which most data analysts are familiar with. They then submit this computation to the info platform, for instance, using an HTTP REST endpoint. Now, this program gets interpreted and gets translated into an algorithm, a privacy-preserving algorithm, which is, in fact, the Speakeasy program. This program then, as we said, gets fed to a scheduler or a PDD evaluator, which eventually schedules and plans the computations and sends the computations over to the players involved, and in the case of our multi-party context, potentially also to the trusted dealer to generate the randomness. At the end of the computation, results are sent back to the analyst directly. And all this is done through these secure channels as depicted here. So what we really see is that a Speakeasy program, if I may allow myself to go back a little bit, really lives in this red rectangle here. That means that a Speakeasy program is actually written by an internal algorithm developer, potentially at Infer. It's not written by a data analyst outside. So when writing a Speakeasy program, you're really inside the platform, and you are you have to think of it as if you're executing it, it's executed by the runtime. What does that mean? It means that we distinguish these two worlds. We distinguish a world which is a PDD of a world and an A world. When writing a program in Speakeasy, the general rule of thumb is if you have values of type A, they will be seen by this runtime. And if you have values of type PDDA, they will be seen by those who own the data involving this PDD and by nobody else. So when you're designing an algorithm and a protocol, which is privacy preserving, as an algorithm developer, you can think of what you can leak or not based on the type of a value.
Okay, so now we've given kind of an intuition of these PDDs being these building blocks of pipelines. Let's look at exactly what they are. So PDD is defined as a representation of some data type A that might be distributed across multiple partitions, where every partition is owned by one party in some kind of privacy-preserving setting. So typically, in a multi-party computation world, this just means between three parties, one person just would not want to reveal their data. PDD also is the result of a sequence of operations. So that means if you have access to some PDD, you can compute the whole computation, so all the operations that lead to it just by looking at it. This is very important to decouple this evaluation from the definition of the PDD. So in short, PDD is the encapsulation of representing where data lives and the ownership. The PDDs that we define in Speakeasy are two different ones. In green, the so-called uniform PDD, this represents some data where every partition is replicated. So this means this is some plaintext data that everyone knows. So if we have, in this example, there's data A shared between three parties, this just means every party has the same view. There's a specific degenerate case where there's only one party that has access to it. It's also a uniform PDD. We give it a special name, private PDD, because it's very common. When you source data, when you instruct someone, say, hey, Alice, read data from this CSV file, it gives you a PDD that has one partition and is also plain text. Then on the other side, we have the so-called secret shared PDDs in red. This represents data where the partitions are now different. They are numeric, and they seem random, but adding them all up will give you some well-known value. The types of operations we define on PDDs can be brought down into three different categories. So there's operations which change ownership, or model the change of ownership, I should say. There's operations which model the change of data itself. And finally, there are operations which force the evaluation of a chain of operations.
Let's look at what that means in real. So on the left, where Jakob stands, is the A world, and on the right, where I stand, is the PDD world. And really, the idea is to say, well, how do we go from one world to the other, and how do we go from one kind of PDD to another one? To start with, you have to be able to create such values. How do you create PDDs? Well, there are many ways you can do it, but fundamentally, they boil down to the following, which is either as a programmer in the A world, you just instruct, you just send a value, like a constant, for instance, to owners, or you can load them from the data owned by each owner, by different people. Sometimes these databases on the right can be shared amongst many people, and that will give you either uniform PDD, or in case if it is also possible that you can have secret shared values, so secret PDDs that get loaded from this database. Another way, simply to create a secret PDD, is to request a trusted dealer to generate some shares. One thing you want to do once you have a PDD is to compute on it. So you want to change its value, for instance. Now, if you're a Scala programmer like us, immediately you would think of the map high order function. And indeed, there is a map high order function which takes a PDD of A, a function and gives you back a PDD of B. Then what you can do is you remain in the world of the uniform PDDs and you change ownership across them. So for instance, if I have a value and somehow my algorithm tells me that it is in my interest to communicate that value in plain text to everybody else, I will use the broadcast function. If I have how do I go from secret PDD to a uniform PDD? Well, I do it using a reveal function. What does the reveal function do? Since we're talking about additive secret shares, basically every single owner will communicate their share to every other owner of the PDD, and each of them will add them up using the additive secret properties to get back, in fact, the original value. We can also go the other way, of course, which is you have data and you want to secret share it. So generally, in our case, you would request the trusted dealer to generate some randomness, which will help you create a secret PDD. So but at the end of the day, you want some value back. And well, before you want some value back, you also want to be able to combine PDDs. Nobody works with a single PDD. You do stuff with different values. And for this, again, a common function programming pattern is to use zips. And there are various kinds of zips that are depicted here, which, based on how you combine them, give you back a secret or a uniform PDD. Finally, you evaluate a PDD, and this is the eval, where from the PDD world, you go back to the A world. And what happens then is when you have a uniform PDD, you just request one of the owners to give the value back. Or if you're a secret PDD, well, you just request all the shares, and again, using the additive secret share properties, you add them up. So this is, that's basically it. That's all you really need. This diagram may look a little bit cumbersome. Of course, we prefer writing it this way. In fact, there is just one trait, which is a PDD trait, which has two subtypes, secret PDD, uniform PDD. You have a player, and you have functions on these. And note that on the left, you have the A world again, where you can eval, and in the right-hand side, you have functions that may give you the possibility to change from one PDD to the other.
Now, this allows us to model the data flow between uniform and secret PDDs. Quick side note is right now we focus on multi-party, and so the only secret PDDs we have are ones that correspond to additive shares. If we incorporate new technologies, this could be represented as different kinds of PDDs. But back to the main topic. So these low-level operations allow you to build protocols to express basically any flow you want that combines any plain text data processing with any multi-party data processing. Now, the danger is you're mixing, in the same language, you can freely mix secret data with operations on data that is intended to be public. This is very easy to shoot yourself in the foot. If you, for example, have some secret data that you need to mask with some noise before revealing it, it's extremely easy to forget that. No type error will prevent you from doing that. So in practice, we actually do not expose all these operations. We expose two main operations. One of them is to work on public data, so to apply some function on a combination of PDDs that are plain text and return another plain text PDD. And then there is the other big operation, which I showed you earlier, the multi-party operation, which itself embeds a language that is specialized to work only on MPC, on secret PDDs, and offers you a completely different language to manipulate objects there. So in practice, if we look at some code again, we can decouple this high-level language into two main constructs. Of course, there's more, but today we're focusing on these two. So there's one operation called the zip map, and there's one operation called MPC. These two are both operations. So what does that mean? That means that they have a reference to some outputs, both of them. They have reference to some inputs, some specific PDDs as inputs, and then they have a payload. The payload indicates, well, the payload is specific on what the operation represents. For the zip map operation, which is a generalization of a map operation, the payload is a function that is applied to every partition of the private distributed dataset. For the MPC dependency, for the MPC operation, sorry, the payload is a little bit more complex. It's basically a representation of this embedded DSL that I talked about earlier. So it means what is this representation? It's a function that takes some MPC context, which will be defined later, a list of inputs, this time viewed as another object, so not as a PDD directly, but as a representation in the MPC domain, and gives us back another list of MPC objects, which will then, as a result, be returned as new PDDs. Now, of course, defining these structures yourself is extremely tedious. So that's why we offer a syntactic layer on top in Speakeasy, which allows you to write these, combine these different DSLs in a very seamless manner. And we will explain in the next part on how these things exactly work.
That's right. So now that you know what PDDs are, let's find out what we can do with such a thing. So what is a PDD graph to start with? So recall that we said that every PDD knows where it came from, so knows the operation from which it resulted. As we said before, if you walk your chain back from a PDD that you want the result for, you can construct the whole graph of everything that led you to there. So this is the graph that you built, and then all you need to do when you want to evaluate a result is to essentially schedule and evaluate this whole graph. Well, of course, there's no single way to do that. You can, given a graph, schedule and execute it in whatever way you deem fit, as long as, of course, the dependencies are respected. I mean, one simple way is to just do it linearly. Otherwise, you can also use some sort of parallel processing techniques, work stealing, and so on and so forth. This is not dictated by you, but it's generally dictated by the system in which you're working. We have an experimental evaluator, which we call Bootleg, of course, to stay in the theme of the Speakeasy. And in Bootleg, we compute a transitive closure of all of the graph that basically gives you the targets. Then you map the closure to some runtime tasks, and you schedule the tasks in such a way that the dependencies are evaluated in the correct order. And we have some notion of parallelism. Of course, at the end of the day, we reconstruct the final result.
Now, just a quick thing before we move on to the final section of this talk is to note, if you are familiar with Apache Spark, this might seem more like a déjà vu to you. Apache Spark is something called an RDD, a resilient distributed dataset, which also encodes a chain of computations on data. And in fact, the name RDD was a direct inspiration for PDD. There are some subtle differences. We won't go too much into detail here, but the gist of it is that PDDs really focus on location. Sometimes here we need to trade off availability for security, so we can't really write this as just a library that just uses Spark under the hood.
That's right.
Yes.
So, but in a nutshell, then, what do we have then for evaluating a PDD graph?
Yes. So the similarities still with Spark stay the same, right? So they still are a lazy representation, and we really decouple the description of our program from the execution. That's really the main thing, except we're doing it in a way where locality and what data actually means is very important. But now, since this is a Scala conference after all, we should talk about what exactly are the features we used to build this language, specifically focusing on combining these different DSLs, the high level and the MPC one.
And we have to say that we had it in Scala, not only in Scala, but in Scala 3. In fact, very early on, we adopted the Dotty, which really helped us with a lot of different features. But so it does help a little bit to explain to you how Speakeasy has evolved. So 2 years ago, we presented an external DSL for privacy-preserving computations. And very quickly, it had to be turned into an embedded DSL. And so today, as we told you, just an embedded DSL for MPC is not enough. We want it to be composite. And compose with other kinds of processing. So what motivated us to go from an external language to the embedded one? Well, here's what the external language looked like. If you look at it closely enough, it looks a lot like Scala 2, and maybe a little bit like MATLAB. So the syntax was very close. We had more semicolons. However, the main difference here is that we just have very primitive types. Matrix, vector, int, that's practically all there is. And on top of that, all the operations you see, which are prefixed by XOR here, they are all built-in operations in our language. So this is very specific to the domain of MPC that we have right here. And we have some basic way of writing functions as well. But I mean, very quickly, what happened was we noticed that it was not enough. Our users internally wanted to do more complicated things. They wanted to use data structures like arrays, maps. They wanted to use classes, case classes, all these kinds of things. And of course, we could build it in our language. As compiler people, we would have enjoyed that quite a lot. But that's not what the main goal of this language is. We want to focus on the domain, which is privacy-preserving computations. So the gain, the trade-off, or the marginal gain of developing all this ourselves has a huge upfront development cost. And Scala is a good language, after all, to build DSLs and embedded DSL. It has many nice features. So since our compiler for the external language was already built in Scala, the transition was not actually that hard. The language looks like this. The embedded language looks like this. Although, as you can see, it looks almost the same as the external one. Of course, now we have vowels, we don't have bars, and we don't have semicolons. Am I missing something, Jakob?
No, not at all. So now let's look at the features that made this, this embedding possible. So broadly speaking, we can boil them into two specific features. And one of them is actually not related to Scala 3 yet. The first one is really purely syntactic. I'll briefly mention it, but it's not the most interesting part. So one of them is top-level functions and import renames. Those features may seem quite trivial, but they really allow us to follow a design of a library that looks like Python. And this is very important if you're working with data analysis tools where the lingua franca is Python, and to avoid or to minimize your context switches. So if you're testing something, comparing something, building a program with NumPy, and then want to switch over to the MPC world to build your same algorithm there to compare it, this really minimizes it. It also allows you to build a library that's very easily navigatable and easy to read. Now, if we implemented everything directly in this very direct manner, unfortunately, we would miss out on a lot of features, and the gains we get in having something linear, we as the developers of the library would probably need to pay in code duplication or in just limited use of abstractions. So this is where the second feature comes in that we've used. And this is what we could say is the structural feature. So it's actually quite simple. It's just passing in a builder as an implicit parameter, in Scala 3, a given. This really allows us to decouple the syntax from any structure of the program we use, because we're using this context to build our, for all the state management for building everything, as you can see in this next slide. So in here, again, this is, if you're very familiar with Scala, this is just using the new syntax for imports. So in red here, in the red boxes, I've just highlighted where this parameter would be passed. We need it explicit. But basically, what you need to know is that any function that is defined as a function using the MPC DSL will take an implicit parameter and call other functions. In the end, all primitive functions will be implemented in the context. So all intrinsics of the compiler, if you will somehow end up calling into the context. And this is where we, as the developers of this library, now get free rein. We can decide to, all the state management, error reporting, some kind of type checking, or other property inference can all be done in this context. The only thing we do is return some kind of node that in the user level will then represent some relation to this context. And so what does this all enable us to do? It really gives us actually a lot of flexibility. So if we assume we create a context, which again will be very highly dependent on the use case, the compilation, which used to be the external language, we would invoke an actual compiler, now just amounts to calling a function and passing in that context. Yet we still get all the same flexibility we had from the external DSL. We can do different things with this context. For example, we can generate some instruction set that target our proprietary MPC VM, which is very efficient. Or we could, instead of doing that, we could generate Python code. In fact, we actually do that. So we can compare the precision of our own system versus what the equivalent algorithm would be if it were using primitives in some fairly popular Python number libraries. And finally, we can also just interpret our code for debugging purposes. But what it also gives us, and this is actually maybe even more important, are restrictions. And it's a good thing. They provide guardrails. So the simple fact that we need a parameter to call an MPC function really allows us to delineate what is a DSL and what is not a DSL. I think often a criticism for some libraries that make heavy use of DSL in Scala is that it gets complicated to find a boundary. When are you using DSL? When can you use regular Scala? Here, this really demarks a boundary. And finally, of course, if you pair that now with an implicit not found and this flat user library, user interface we wrote, you can get very good error messages that really make you feel like you're working with an external DSL.
So that was so we went from an external DSL to an embedded DSL. And then we thought that we realized it was not enough. MPC was not enough. So we needed to go composite. And why do we need to go composite? Well, we need to express higher level data flows. And we also want to be able to do it in one single place. That is one single Scala file or one single Scala package, Scala library, instead of having to mix and match with other external dependencies. And of course, the other requirement is that since our embedded DSL for MPC targets the proprietary VM that we have for efficiency reasons, we also needed to keep it that way. Since we also had users who had been trained for using this DSL for a long time and were very good at using the DSL. So what we need is really a way to compose languages, right? And it can be sort of seen at the bottom here. We want to be able to, at a high level from the outside, say that I switch contexts, but inside each of the boxes in the triple dots there, you do whatever is specific to that context.
So how can we do that? This is now where we actually use some features that are really, I think, noteworthy in Scala 3 that allowed us to do this. So this is namely context functions and macros. So a context function is just a lambda, essentially, that we do not need to declare the parameters when you can pass it along. And it allows you to basically apply the good old functional programming trick. What you do if you need to pass in state somewhere, you capture it in a lambda. Except now we don't need to declare the parameters. And macros give us a lot of power in the way we derive some kind of structure. We can basically introspect syntactic, so we can introspect user code and do what we want with it. So it's going to be a key ingredient to building a DSL with a perceived low complexity. So let's look at how these two features work, in how we've used them. So we'll start by looking what we would like the user to be able to write. In a general flow, again, it's PDDs, the algorithms you express are often fairly linear. So here in this example, we just have two PDDs we assume exist somewhere. And then we want to use them in a multi-party computation. And inside of here, remember, this is a different language. So what we do is we view every outside PDD, we can view it as a matrix, which again is this virtual object specific to this language in here. Same goes with the other inputs. So we want to kind of capture those things. And then we want to map a result of some other type here to the PDD world. So if we look at the structure, in a sense, we want to build these operation classes where we automatically create an output, find the inputs, and compile and transform the user code into the payload that's expected by the PDD dependency. And our interface to this is basically by defining an API that precisely uses context functions and macros. So how do these two things work? Now, as we just talked about, the context parameters, they would usually have to be declared somewhere. With a context function, which is demarked by the question mark equals greater than, this means that you do not need to declare the context, but it will basically, your multi-party, a context will be declared here. You do not need to declare this parameter yourself. So that allows us to inject this limit of the DSL here without the user needing to specify it. And then the macro. So the inline keyword followed by a macro, which would be on the right-hand side, allows us to basically traverse the body. So we can introspect the body, find all references to outputs, so we can then use that to define this, define them in the structure. And then finally, this is actually something called a white box macro. So that means the return type of the macro will actually, it can be, does not need to be declared here in the definition of the macro. It will be inferred at expansion. So this allows us to map this custom matrix type back to whatever uniform PDD, or whatever PDD it is here. So you'll note here, if we have a public matrix, it becomes a uniform matrix. Secret matrix would become a secret PDD. In a sense. But in general, I think really the key insight from this is that we are abstracting structure from syntax. Really, that's really the key thing. It allows us to build a DSL that has a perceived low complexity for users, but we can still drop down to the structure if we need to manipulate those objects because of a bug or any other reason. If you want to know more about these patterns, I gave a talk here. You can watch it if you're more interested in diving into the deep depth there.
So that's right. What we have achieved with this attempt at Speakeasy with composite DSLs is the ability to compose privacy-preserving techniques. And in fact, right now we support MPC and Gabel circuits, along with, of course, all the local processing that needs to be done around it in order to make privacy-preserving protocols. We also have made some experiments with federated learning. They are early experiments, and we hope that we hope that it becomes something very interesting to use in conjunction with the techniques already. Now, since we have a composite way of doing these things, we can attack other privacy-preserving techniques, like homomorphic encryption, for instance. But even more interesting than that, from a compiler or language point of view, is the idea that you can, since you have a whole view of a program, actually track which values are being revealed to whom when. This allows you to think of things like a privacy budget, for instance, and given a program, perhaps allow to do some sort of static analysis that tells the user how good their privacy-preserving algorithm really is in terms of leaking data or not. For now, of course, it remains something that is a little bit of an art, not yet a science, and this is where our algorithm team and our team at Infer really helps us in this regard.
If you would like to play with this library, there's only so much you can put into a 45-minute talk, but we have many more examples available in a hosted environment. This environment is basically a hosted Visual Studio Code editor in the browser, which has a runtime setup and some sample data with a bunch of examples, and also an exercise, which is a game in which you need to define a protocol for two armies to battle, but they, without revealing the numbers of the armies. So they actually do not fight each other, but they would like to know the outcome without revealing what units go into battle. So if you're interested in trying that out, you can go to this website, you can register, and then you'll have access to this hosted environment to play around. One thing to note, however, is that you might need to wait 3 to 5 minutes if the environment is ready, but then everything should be pretty smooth.
What remains for us to say here is that really, while we are talking here from Infer, this is really a team effort. And the reason we've made so much progress in such a short time is because we're fortunate to have users from the very first day. The algorithm developers at Infer have constantly given us feedback, and that has really helped us improve the language. And to the point where actually today they take the lead when it comes to designing DSL features and a lot. And just like the team at work, this presentation has also been a full team effort. So we'd like to thank all the people at Infer who have helped us there. If you'd like to join this team effort, please let us know, and we'd love to have you. We'd love to listen to what you want to do with us.
So then, of course, thank you, Scala Center, for all the advice, especially Vincenzo, for all the advice on the green screen that you see behind us, and all the audio visual equipment. And
actually, Vincenzo is sitting behind us, and so we're very happy to have him help us with the talk and direct the whole thing. Merci beaucoup, as they say here in Switzerland, despite it being virtual, so we are here. And again, please go and try it out and let us know what you think.
Feel free to either reach out to us if you have any problems also with the hosted environment, either by email, or we'll also be on the ScalaCon Slack channel and watch for mentions there.
And from now, we take questions if you like. Thank you.
Yes.
All right. Thank you both so much for that talk. And we'll jump into questions. I think we've got at least one question for you. So here it is. What MPC engines are supported by Speakeasy today? Is PDD idea somehow related to federated machine learning?
So the first part, the engines we support are actually only our own virtual machine. And then the plain text equivalent, which basically simulates these algorithms using some Python libraries.
That's right. And how is it related to federated learning? Well, the relation is something that we're exploring right now. So PDD by itself is not related to federated learning. It is more a way of thinking about data and ownership, which you can use to model federated learning computations as well. And we have, as said earlier in the talk, some experiments with it. We're doing it.
Fantastic. Well, thank you so much. And I think that's all the questions we have. So thank you both for your talk today. And thank you for being the sharpest dressed individuals at ScalaCon, I must say. And enjoy the rest of the conference.
Thank you.